Welcome to Section 3 of AP Calculus. A lot of what we're going to talk about today is just notational. This is derivative of a constant with respect to x. That's how we would read this. And oftentimes it's dy dx. And d, for whatever reason, and maybe it's Latin-based, oftentimes stands for the change of. So this is change of y on change of x, and that should sound very familiar to you. Y minus y over x minus x, this is just slope. So we're going to talk about we're going to use this notation, but this is really no different than f prime of x as we've been referring to our derivatives, or our slope formulas. But we've got other ways that we're going to express derivatives as well, and we have to be familiar with all. It's kind of like, we go to Mexico, it would help if we speak Spanish. We go to Canada, it would help if we speak Canadian. All right, one person laughed anyway. We got to be able to speak the different languages. So we're going to use dy dx. This will be read derivative of y with respect to x. So this is derivative of a constant as with respect to x. Okay, so the derivative of a constant, this is just silly. This is like saying f of x equals 4. What's the derivative of 4? And it's insulting if we understand that a derivative is the slope, and what's the slope of 4? 0. The slope of a constant, the constant function, any constant is a horizontal line, therefore has a slope of 0. So the derivative of a constant, if c is a constant with respect to x, is 0. Okay, simple. If I said f prime of x here, that would be 0. All right? Power rule. This is hugely liberating. The power rule says the derivative of x to the nth with respect to x. This might as well just say f of x equals x to the 6th. Says the derivative of that is, well, the n that was here now is in front. The x is still there, and we reduce n by 1. So the slope formula for this is the 6 comes out in front, and we reduce it by 1. That's just an example of that. Is that all right? And then they tell us this is a special case, but this is just silly. The derivative with respect to x is, we can think of it as derivative of x to the first with respect to x. Bring the 1 out in front. Change this to 0. Oh, x to the 0th is 1. 1 times 1 is 1. But how silly, how insulting. This is saying, what's the slope of x? What's the slope of the line y equals x? It's 1. Right? No problem. Don't forget, we got roots in this stuff. We know what derivatives of lines are. And that ends up causing people more problems than the challenging derivatives. I'll bet we get a question on it a little bit later on. Where'd that come from? We'll see. Okay. If u is differentiable function, well, what does that mean? Well, that's a 3-1 topic. When is it differential? But it's really, really simple. All right, we will talk about when it's differential, when something's not differentiable. It has a lot to do with limits and continuous functions and those kind of things, more of the language. And c is just a constant. And u is a function. So this isn't a constant times a constant. This is like 2 times x squared. This is like 3 times log of x. It's just a constant. Look what happens. We can just pull a constant out. Why? Because what's the constant do? It makes it c times as tall. That changes its growth rate by a factor of 3. It's 3 times, y is 3 times as big. So our change of y is 3 times as big as our normal change of y. Does that make sense? All right. So we can just take the constants out. So that's like saying if f of x is 9x squared, then f prime of x is just 9 times x squared prime. Thank you. It's just 9 times x squared prime. Right? I don't take the derivative of 9 times the derivative of x squared, because that would be 0. It's 9 times the derivative of x squared. Okay. In special cases, this isn't a special case. Negative is just a constant 1. Pull the negative 1 out in front. This isn't a special case. C is just a constant. Pull it out in front. We don't need a special case. However, this is ultimately, actually it should be the whole thing, is ultimately maybe our MVP of everything we're going to do for a while here. If I've got a constant, so this is like f of x equals 3x to the 5th f prime of x would equal, what do we do? Well, we really just take the 5, pull it out, bring the 5 down, take the 3, pull it out, bring the 5 down, x reduced by 1, 15x to the 4th. Now, here's a trap people might get into, and I'm taking points off for it. If we're trying to find the derivative and you just say, oh, well, this equals 15x to the 4th. No, it doesn't. They're not equal. The derivative is not equal to that. Right it is the derivative is. But you see how that could happen. We got to communicate effectively. Any questions there? This is really the power rule with a constant. That one is going to be, boy, if you had to, if you want to fail the next test, forget that rule. You have no chance. Okay. Then we have some other special rules. If this is like f of x plus g of x, this would be similar to saying this. If I had a function of x plus another function of x and I wanted to find its derivative, I could just find the derivative of the first function and add to that the derivative of the second function. It's like it's distributable. Is that okay? It's just what you would think you would do. It's another one of those rules. Likewise, if it's subtraction, a function, derivative of a function minus a function is derivative of the first function minus derivative of the second function. Easy enough. It's just what you would think it would be. However, product rule is not just what you would think it would be. You would hope maybe that this is just either derivative of u with respect to x times b, or maybe it's derivative of this, derivative of u times derivative of v. You would hope it's not. This would be this way. If I have a function of x times another function of x, and I was taking its derivative or finding its slope formula, it is the first function stays the same times the second function's derivative, plus the second function stays the same times the first function's derivative. Now, just to clarify here, does it matter whether I do this first or this first? Can I switch those? Is a plus b equal to b plus a? Yes. In fact, could I switch these? Could I go g prime x times f instead of f times g prime? I'm only saying that because my habit is this. My habit would be to say it's f of x times g prime of x plus f prime of x times g of x. They're equivalent. Isn't that clear? These two are equivalent. We can multiply in either order. I'm going to try to be on board with how the book does it, so we're all checking with one another. I'm going to try to do it this way, but it's hard for me to imagine at some point I won't fall back into old, very, very ingrained habits. All good? All right, quotient rule. Ooh, that's a mess. If I'm taking the derivative of a function divided by a function, I take the denominator and multiply that by the derivative of the numerator minus the numerator times the derivative of the denominator, and then I divide by the denominator squared. Well, wouldn't it be nice if there was a good little poem for this? We remember that one? We call u our high function, and we call v our low function, and we call the derivative of the high d high, and we call the derivative of the low d low. Here's what we got. Low d high minus high d low And we could say over low squared, but then it wouldn't rhyme. So it's low d high minus high d low over the square of the thing below. You might want to write that down. Every time I do a quotient rule, I say it in my head. So low d high minus high d low over the square, not the square root of, over the square of the thing below. What do you suppose the most does it matter if I switch these two? Does it matter? What if I go high d low minus low d high? Yeah, it matters because it doesn't rhyme anymore. But does it matter? Yeah, a minus b isn't the same as b minus a, is it? Product rule, just so long as you don't go derivative of first times derivative of second plus just plain first, just plain second. So long as you got one of the derivatives in each one, you're fine. So low d high minus high d low over the square of the thing below. This would be the same as saying if I had f of x on g of x and I was finding its derivative, that would be low, well, I'm going to run out of room here, d high, that's bad, running out of room, where am I going to put it? I'm going to transport this guy down to here. Low d high minus high d low over the square of the thing below. That's the notation you might be more comfortable with than this. All means the same thing. Low d high minus high d low over the square of the thing below. That's how we want to handle this. Okay, so we're going to find the derivative of, and we're going to use this notation for a while. We got to get comfortable with everything so we can go to Canada. dy on dx just means the derivative of. The derivative of x, how insulting. The derivative of x is the slope of x. It is 1. Now I could do limit as h approaches x of x plus h minus x all on h and go through that process, but we know it's 1. What do you suppose this is asking for? This is just asking for the second derivative of y with respect to x. Second derivative of y with respect to x 2 times. That's all it's asking. So this is asking for the derivative of the derivative. That may ring a bell to some of you, the slope formula of the slope formula. You took a test in honors pre-calculus last year that had you find the slope formula of a slope formula early on, chapter 2. So what's the slope of 1? How insulting, it's 0. Okay. Now, why would we find the slope formula Well, the slope, let's say we were dealing in, this is hours, and this is miles. Do we understand our slope is miles per hour? And no, can't cheat, physics people, don't just yell it out yet. If I take the second derivative, it's miles per hours per hours. Miles per hour squared. Miles per hour is change, is rate of change, right? It's typically a speed, miles per hour. So the derivative of that would be the change of speed. I went from 20 to 27 miles per hour. What's our word for change of speed? Acceleration. The second derivative is acceleration. The third derivative, I want to have a t-shirt that says, don't be a third derivative. Third derivative is change of acceleration. Now we're thinking on a much deeper level. So if I just held my hand out in front of myself still, that has no acceleration. Now understand, as I walk with my hand out in front of me and I walk at a steady rate, that has no acceleration, right? It has a constant speed, it's not accelerating. Now, if I take my hand right out in front of me and I begin to move it to the left, it's accelerated. It's went from still, it's accelerated on the way. But it's gradually accelerated. It's accelerated on a curve. Now, if I take my other hand in a fist, and let's say I'm going to punch this hand at 15 miles an hour, it's immediately accelerated from 0 to 15. Instantaneous acceleration jerk. It's called jerk. The third derivative finds a jerk. Don't be a third derivative. All right. That is the true name for the third derivative. It is the jerk. Okay. It's a good movie. All right. You guys ever see The Jerk with Steve Martin? It was like Steve Martin's breakout movie. Oh my gosh. It's better than Dumb and Dumber. Or close. All right. So first derivative, dy dx equals. We could do limit. This wouldn't even be too bad. Limit as x approaches, or as h approaches 0 of the opposite of x plus h squared, half to FOIL, half to distribute, plus 3, minus parentheses, negative x squared, plus 3, have to distribute the negative, have to combine, cancel an h, and we would find out that that is negative 2x. So I just saved probably a minute. Probably a minute. Reasonable? Second derivative. This would be easier. I could go negative 2 times quantity x plus h minus negative 2 all on h, and that would take me 30 seconds, but the derivative of negative 2x, excuse me, is negative 2. All right, finish C through D. Try these. If you're at home and you don't want to try them, you can fast forward. Quick comment on D. Eyes up here just for a moment. Do we need to quotient rule these? You could go low D high minus high D low. What option do we have to that? We could rewrite this as 1/3 x cubed plus 1/2 x squared plus x. See how that changes maybe our approach to it? Okay. I'm going to give you only, because that's all it should take, I'm going to give you about a 60-second head start. If it wasn't for music laws right now, I'd play Pandora over the top of this, but I can't put that out on YouTube. Anybody thinking right now that you guys should shop for me for a new rubber stamp? It takes longer to do what I just did than it does to find the derivatives, I think. All right, so from this point on, when I go through derivatives and I look up, if you got the same thing, your finger is touching your nose like you're playing spoons, right? Okay. Derivative of 2x plus 1, 2. Derivative of 2, 0. Okay, if you're not touching your nose, not playing along, I think you don't understand. Good. Derivative of this guy, 3 times 1/3, 1 times x, reduce it, x squared. 2 times 1/2 plus 1 times x. Don't have to have the 1 there, of course. And derivative of x is 1. Let it be known that everybody's touching their nose almost. Okay. Derivative of x squared, 2x. Derivative of 1x plus 1 plus 1. Save you the embarrassment. This is where the question came. Okay, I get how you got to here. How'd you get to there? Well, what's the derivative of this? It was like I get where the 2x comes from. Where's the 1 come? We forget where we came from. The slope of a line. The slope of this line is 1. Okay, derivative here, 8x minus 8. Fingers. Good. Fingers on nose. And the derivative of 8x minus 8. 8. Questions there? Simple, simple. Okay. Find all derivatives. When they say this, I believe they mean just take it and... Did I forget E? I forgot E. Forgot E. I left you hanging there. Oh, this is a good one, too. Because what if we had to do this one with limits? Limit is x plus h to the fourth minus 7 times x plus h to the third plus 2x plus h to the second plus 15 minus parentheses x to the fourth minus 7x to the third plus 2x squared plus 15. Super duper foil, superfoil, foil, distribute, distribute, distribute negatives, combine, cancel your h, or just say it's 4x cubed minus 21x squared plus 4x. This is Independence Day. Fingers. Yep. And the derivative of that. Oh, no, it would be a lot quicker now. X plus h, x plus h, x plus h, minus parentheses, all of it. Or 12x squared minus 42x plus 4 fingers. Very good. All right. So back to example 2. I believe they just mean keep taking the derivative until you get to 0 here. Let's just do this second derivative as well. Give you a 40-second head start. It really does take longer to do that part. Okay, A, 2x minus 1 and 2. Fingers. Let's point forward. B, did we treat this like quotient rule? Watch this. If I treated just this first one like quotient rule, let's go through that. Low, D high, times 4x cubed, right? Minus high, x to the fourth, D low, 0. Over the square of the thing below, is that all right? I would get 8 divided by 4, 2x cubed. But if I bring the 4 down, I get 2, yeah, 2x cubed. You with me there? You can do it, but if we don't have to, I wouldn't. Bring the 2 down, cancels the 2, minus 3x, minus 1 fingers. All good there. Derivative of this, 6x squared minus 3. Because negative 3 is the slope of negative 3x minus 1. Okay. Quotient rule. Quotient rule, however, there is a workaround to this one. There's not a great workaround to this one unless you use chain rule, and we haven't taught chain rule yet. We taught chain rule last year, and that's where that was those of you who had me, I think for sure will remember, probably Mr. Hartz. I'll get a nod from you that had Mr. Hartz to talk about for chain rule, you treat the mother, wait for the baby to be born, then treat the baby. Yeah, so we haven't talked about chain rule in here yet, but we will. But there is a workaround for this one. C, let's just do A and B, then I'll prep you on C a little bit. Quotient rule, quotient rule. You can look it up, or you can remember the poem. Low D high minus high D low over the square of the thing below. We're just finding the first derivative. Give you about 30 seconds. Oh, these simplify in the numerator pretty nicely. So let's simplify numerators. Just A and B. I guess if you're adventurous, you can try C. Low. I hope you get in the habit when you bring the low up, if it's more than a monomial, you put that thing in parentheses, because typically it's going to be multiplied something other than 1 D high. See what I'm saying? If this was 2x and I put the 2 there and I don't put the parentheses, I might get x plus 14. So low d high minus parentheses high d low is 1 as well, all on the square of the thing below. Or, let's see, this is x plus 7 minus x plus 1 on x plus 7 squared. How about fingers if you ended up with 8 on x plus 7 squared? Thank you. Okay. Let's go chain rule with this, and then I'll show you the alternative. Low monomial, don't need parentheses, d high times 3x squared minus high, need parentheses, x cubed plus 7 d low times 1, all on the square of the thing below. Let's simplify this. We'll do it in one step. Let's see. I get 3x cubes minus an x cubed for 2x cubes, and I get a minus 7, all on x squared. Questions there? Now, we know we could write that as 2x cubed, on x squared minus 7 on x squared, or 2x minus 7 on x squared. And I'm not saying this is more simplified than that, but I want to show you an alternative to this. Is that okay? All right. This could be rewritten as x squared. This is actually equal to x squared plus 7 on x, right? But x squared plus 7 on x could be x squared plus 7 times x to the negative first. Is that okay? Let's power rule this guy. This guy's derivative would be 2x, bring the negative 1 out in front, minus 7x to the negative second. Is that okay? Same thing. All right. I noticed we got a product, and let's say we can't FOIL for whatever reason. We're not going to super FOIL this out, because maybe this would be sine of x times, and then we're going to get sine of x all over the place. We're not always going to. It's not always going to be polynomial. So let's say we cannot super FOIL, or it's inconvenient to. So we got a product, and we got a quotient. And we got rules for products and rules for quotients. What we have to determine is this in the big picture a quotient, or is it in the big picture a product? Is this a product with a quotient built in, or a quotient with a product built in? It's a quotient with a product, right? So we're going to quotient rule this. Oh, that's good. We get to say the poem. Low, well, that's easy. D high, yikes. Minus high, that's easy. D low, that's easy. Low, easy. D high, yikes. Try it. Give you a 60-second head start. No simplifying when you're done. It's a quotient with a product, D high. low, d high, yikes, first times derivative second plus second times derivative of first, that's times 1, low, d high, minus high just as it was, d low is a breeze, 3x squared, all in square, another thing below x to the 6th. Questions there? Fingers on noses, got it right? Got it? Okay. Now, earlier I mentioned sine. I want to talk real quickly about sine, just because it's kind of interesting. Then we're going to go to the back page for a second. As it turns out, sine of x's derivative is cosine of x. Now, immediately, if you didn't work on this last year, don't remember from last year, you all should be saying, oh, this is going to be easy then. Cotangent's derivative is tangent. No, cotangent's derivative is negative cosecant squared of x. Oh, secant's derivative should be cosecant. No, secant's derivative is tangent of x times secant of x. It's not, but sine is cosine. Oh, then cosine sine. No, cosine is negative sine, of course. No, it's not one size fits all. But here is the graph of sine, first period. Something like this. Now, if I start talking about, this isn't going to prove it to you, because there's some discussion that needs to go on here with it, but the steepest the sine graph ever gets in slope land is 1, and it happens right here. That is a slope of 1. So if I graph that, at 0, the slope is 1. Is that okay? I'm just graphing the slopes as we go. And somewhere along the line here, we get to a half. Somewhere in here, we're at a half. And the slope there, I don't know what it is. But I know what the slope is here, right? The slope here is 0, right? And then the slope goes to a negative phase. So the graph of the slope would be below 0. Until it gets to here, guess how steep it is right here? What's the slope here? Well, if it was 1 here, it's probably negative 1 there. And then the slope gets back to 0. And now the slope's positive until it gets back to that 1. And we could fit this curve, and maybe it doesn't fit exactly. This is not a proof, but at least that's somewhat believable then, that, oh, the derivative, here's sine, its derivative is cosine. If we graph all of its slopes at any instant, find the slope here, must be that. Find the slope here, must be that. Find the slope here, must be down there. Slope here, must be down there. The slope is negative. Okay, that was just a little filler. All right, now if you're really sharp and have a great memory, you should be tempted to do this with chain rule, because I got a baby function, 1 plus x squared, inside a mother function, x to the negative first. However, we don't have chain rule at our disposal, so let's treat this as 1 minus x. How about this? On 1 plus x squared. That's what y equals. Same thing, right? And now we can quotient rule. And we can quotient rule. And we can quotient rule. Let's see how we handle that square root of x, though, because I'm going to go back to the front page, and I'm not going to see a rule for square roots. I have other rules that might apply. Again, 60-second head start, 90-second head start. Let's go simplify if it seems real easy to do. Here's something I want to point out. Every single time you do this, you may be tempted, but it's going to happen all the time. Look at this. Do I cancel? Can I cancel? It's going to be presented every time, and if it was presented every time, don't you think they would have made a different rule for quotient rule? Don't you think they would have just said, oh, just D high. Don't bother with low, because it's just going to cancel, and don't square low because we could cancel it. It would just be high minus low D high over low. No, we can't cancel this. This is part of a term, and we all know that, but we did not all demonstrate that on the last test. I saw terms canceled. I would say once is way too many, but I saw it really, really, really way too many times. Okay. So, touch nose if we got at least to there, first one. Everything exactly as it appears. How about here? Low D high minus high D low over square thing below. How are we going to handle this square root? X to the half power minus 4. Can we handle that then? Low x to the 1/2 minus 4. D high, derivative of 10, 0. Insulting. They should even ask. Minus high, 10. D low, derivative of x to the 1/2. Same rule applies. Bring it down in front. Reduce it by 1. No big deal. Same rule applies. All on the square of the thing below. So can I just turn the thing below, since I squared it, into x plus 16? Square this, square that? No, you have to FOIL. We know that. It's silly of me to ask if I hadn't just graded your tests. I know we didn't have this, but I had a lot of people have something like this and just square, square. Can't do that. All right, this is definitely worthy of cleaning up at least a little bit, because this is 0. Negative 10 times 1/2 is 5. I'm going to put that on the square root of x all over square root of x minus 4 squared. That's at least a little bit cleaner. Okay. Questions there? Okay, it's homecoming. I want you to have fun, and some of these are going to be extensions. You might have a problem like this, and it's like, what's the tangent line when x equals 4? Oh, 4 would be, yeah, 4 would be okay. When x equals 4, what's the equation of the tangent line at 4? So then you'd get to here, you'd put 4 in here, you'd put 4 in there. We figure out when we put 4 in here what the ordered pair is, and then we, it's an extension on this. But everything in 2 through 22 should be manageable and probably within 20 minutes of when you start it. All right? Won't be here tomorrow, won't be here Friday, but tomorrow you're just going to work on this mechanics again. Okay.